Hello everyone, and welcome to our calculus notes for Rolle's theorem and the mean value theorem. So today's going to be fairly theoretical, and Rolle's theorem says let f be a function that is continuous on a closed interval, a and b, and it's differentiable on the open interval, a to b. So continuous and differentiable. Now what we're saying here is if f of a equals f of b, then there's at least one number c in that open interval such that f prime of c equals 0. Now let me show you what that means graphically. Okay, so here is our interval from a to b, and we're going to have some function going somewhere on that interval, and it's going to be differentiable and it's going to be continuous. Now what we're saying here is if we have a value f of a and it equals the same value f of b, okay, so you can see there that these guys are at the same height. What that's telling me is that somewhere on this function we're going to have a spot, the derivative of the function is going to equal 0. So there's going to be some sort of c value here where the derivative at c is going to be equal to 0. And so basically we get a tangent line here of 0. So in example 1, we want to be able to find the two x-intercepts of our quadratic function, x squared minus 3x plus 2, and then show that f prime of x must equal 0 at some point between those two intercepts. So again, to find intercepts, we're just going to set our function equal to 0, and we're going to go ahead and solve. So we factor this here, we get x minus 1, x minus 2, and so here x equals 1, and x equals 2. So what this is telling me is that f of 1 equals 0, and f of 2 also equals 0. And so this is where Rolle's theorem comes into play, because f of 1 equals f of 2. Let's go ahead and look at this on the graph. We get the point 1, 0, and 2, 0. So Rolle's theorem is going to show us that f prime of x is going to equal at some point between these two intercepts right here. Okay, so let's go ahead and find that here. So first off, we know, because this function is just a polynomial, that it's continuous, and we know it's also differentiable. So by knowing that the derivative is 0 at some point between here and here, we know we're going to get a relative min or max between 1 and 2. So let's go ahead and find that value c where that happens. So we're just going to find f prime of x. That equals 2x minus 3. And then we need to find a critical number, so we're going to let our derivative equal 0. And in this case, we get x equals 3 halves. So we know that at x equals 3 halves, oops, right there, we're going to have a max or a min. So let's go ahead and find f of 3 halves and just plug it into your equation. So 3 halves squared minus 3 times 3 halves and plus 2. So here we get 9 fourths minus 9 halves plus 2, and that equals negative 1/4. Okay, so what that tells me then is right here at negative 3 halves, we have the point negative 1/4, and we would get our graph would look like this. And again, you'll notice here that f prime of 3/2 equals 0. All right, let's move on to example 2. So here it says let f of x equal x to the 4th minus 2x squared. We want to find all the values of c in our interval -2 to 2 such that f prime of c equals 0. So first what we need to do is find f of -2 and f of 2. So we'll just substitute this in here, -2 to the 4th minus 2 times -2. Okay, what we found here is that f of -2 equals f of 2 because they both equal 8. So that means Rolle's theorem applies, and we're going to get at least one value that gives us a derivative of 0. So let's go ahead and find what that is. So f prime of x equals 4x cubed minus 4x. We'll set it equal to 0 and then solve. So we could factor out a 4x, and we're left with x squared minus 1. Okay, the 4 doesn't really matter. And then we'll factor this, x plus 1, x minus 1. And so we actually have 3 values, x equals 0, 1, and -1. Okay, so these are the values of c where our derivative equals 0. Let's go ahead and just find our mins and maxes here. So let's find f of 0. So that would be 0 to the 4th minus 2 times 0 squared, which is 0. Let's find f of 1, which is 1 to the 4th minus 2 times 1 squared, which is -1. And let's find f of -1, which is -1 to the 4th minus 2 times -1 squared, which also equals -1. Let's go ahead and plot our points here. So we know we had -2, 8, and we know we had 2, 8. And let's see, we got 0, 0, 1, -1, and -1, -1. All right, and our function is going to look something like that right there. All right, let's move on. All right, our next theorem is called the mean value theorem. And it says if f is continuous on a closed interval and differentiable on an open interval, then there exists a number c in that open interval such that f prime of c, or the derivative at c, equals f of b minus f of a over b minus a. Now, geometrically, the theorem guarantees the existence of a tangent line that is parallel to the secant line through our 2 points, a f of a and b f of b. So here is what that looks like. Here is our value a, and here is our value b. And let's go ahead and just draw some function right there on our interval a to b. Now, what this theorem is guaranteeing is that at some point on this interval, we're going to have a tangent line that's parallel to the secant line. Okay, so here is your secant line. And if we kind of look at this, we can see if we draw a parallel line that's also tangent to this right here, that we can get a tangent line that's parallel to our secant line. And this would be our value of c right here. So this is what that theorem is saying. And you'll notice, if we look at this right here, the f of b minus f of a over b minus a, that's showing the slope here of this line. And it's saying that it's going to equal the slope of the tangent line. So in terms of rates of change, the theorem implies there is a point in the interval where the instantaneous rate of change equals the average rate of change over the interval. In this example, we're given the function f of x equals 5 minus 4 over x. And we're asked to determine whether the mean value theorem can be applied on the closed interval 1 to 4. So what we're really trying to determine is f of x equals 5 minus 4 over x continuous and differentiable on our interval 1 to 4. Well, if we look at this, this is a rational function. The only place this would be not continuous is where 4 over x equaled 0, which turns out to be just at x equals 0. But we ask ourselves, is x equals 0 on the interval 1 to 4? Well, it's not. It's not on our interval, so therefore we know it's continuous. Now differentiable, okay, it's also going to be differentiable on the interval because our derivative will have the same property where it doesn't exist at x equals 0. So what do we need to do from here? We need to find all values of c in our interval such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. So our first task is going to be just finding this, and this is just our theorem that we had looked at earlier, and we just substituted the 1 and the 4 in from our interval. So let's go ahead and find f of 4. That's going to be 5 minus 4 over 4, which is 4. And let's find f of 1, which is going to be 5 minus 4 over 1, which equals 1. Okay, so these gives us the points 4, 4, which is right here, and 1, 1. And let's go ahead and find f prime of c, and substituting in our f of 4 and our f minus 1 right here. So we get 4 minus 1 over 4 minus 1, which equals 1. So if we look at this, it should make sense, right? Because if we look at the secant line through these two, what is the slope? Well, the slope here is 1. And that's what we're finding when we do this equation right here. We're finding the slope between the 2 points on the graph, and that's 1. Now, what the mean value theorem is saying is that this derivative f prime of c says there's going to be some point on our function that has the same slope as this. It's going to have the slope of 1 as well. Well, what we need to do is go ahead and find what that c is. So we need to find where f prime of c equals 1. Okay, to do that, we just need to find f prime. So let me rewrite our f of x equals 5 minus 4x to the negative 1. Now we can use the power rule. So f prime of x is going to equal, well, negative 1 times negative gives me positive. So we have negative times negative 4. And this is going to be x to the negative 2. And I'll just rewrite this now as 4 over x squared. So what we need to be able to do is find what value of x is going to give us 1 right here. So I'm just going to set this equal here. So 4 over x squared is equal to 1. And we can see that will be 4 equals x squared. And if we take the square root, x is going to equal plus or minus 2. But remember, we're in the domain 1 to 4. So this is going to tell us that c has to equal 2. And just for our graph, let's go ahead and find what f of 2 is. So notice that answers our question of what values of c work. So we answered the question, but let's graph it. F of 2 is going to equal 5 minus 4 over 2, which is, let's see, 5 minus 2 is 3. So that gives us the point 2, 3. So I'm going to go ahead and put that on our graph here. And so our function actually looks something like this right there. And if we look at the tangent line right there, it will also have a slope of 1, just like our secant line did. And then we can see that these guys are parallel right here. So that's determining if we can apply the mean value theorem, and then how to find our value of c, and then what it means graphically. In our next example, it says 2 stationary patrol cars equipped with radar are 5 miles apart on a highway. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. So first let's sketch out what's happening here. So here we have a patrol car, and then we have a 5-mile stretch of road, and then we have another patrol car, and then we have a semi-truck driving along the path here. Put some lights on top of that car. Now let's go ahead and label it. We know that the two cars are 5 miles apart right here. And we're going to let the time when the semi passes this patrol car equals 0. And we also know that the time elapsed for this whole journey was 4 minutes. So we're going to let t equals 4 minutes happen here. Now, because this was in minutes, but our speeds were in miles per hour, we're going to change this into hour. So it's really got to be 4 over 60, which is 1/15 of an hour. Now we're going to let the truck's position be this function s of t. Okay, so this is the truck's position. And we don't know exactly what this function is, but it just looks like any other normal graph. It will go up and down. And we can see that it's going to be differentiable and exist on the entire interval from 0 to 4, or 0 to 1 over 15. That's our interval right there. So if we want to be able to use our mean value theorem, remember, we need to find where s prime of c equals s of 1 over 15 minus s of 0 over 1/15 minus 0. So there is our mean value theorem. So it's saying at some point on that interval, there's going to be a point where s prime of c is equal to this right here. Now you can probably see this as the average rate of change. So this is going to be how far the truck traveled over how long it took the truck. So that's our average velocity right there. So let's go ahead and find that. So we know s of 0 is going to equal 0 because he hasn't traveled anywhere. And we're going to know s of 1 over 15 is going to equal 5 miles. So let's find the average velocity, which is going to be 5 minus 0 over 1/15 minus 0. So we get 5 over 1/15, which equals 75 miles per hour. So since we were asked to prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes, we know if the average velocity was 75 miles per hour, then at some time the instantaneous velocity, which is s prime of t, also must have been 75 miles per hour, which exceeds the speed limit of 55. Well, those are our notes on section 3.2, Rolle's theorem and the mean value theorem. Thanks for watching, and we'll see you in class.